Hello everyone, welcome to Probability and Statistics for Data Science. The central limit theorem is a fundamental result in probability that states that sums of independent quantities are approximately Gaussian. This is used all over the place in probabilistic modeling and in statistics, but we have to remember that it only holds if the quantities are actually independent. So today we're going to provide a cautionary tale about what happens when the underlying assumptions do not hold based on the 2008 financial crisis. Let's get to it. We're going to talk about the financial crisis and the central limit theorem, but before, let's remind ourselves what the central limit theorem actually states. The central limit theorem says that if we have a sequence of independent random variables with mean mu and variance sigma squared, and we look at their average, the sample mean equivalently, the mean of that average or sample mean is going to be equal to mu, which is the mean of each of these individual variables, and the variance is going to decrease as 1 over n. The statement of the theorem is that as n grows, we can approximate the distribution of the average as being Gaussian with that mean and that variance. But crucially, this only holds if these quantities represented by random variables are actually independent. In order to illustrate that, we're going to look at an example based on the 2008 financial crisis. In particular, we're going to imagine that we're a financial institution that has some mortgages. I had to actually stop this video and go look up how you pronounce mortgage, because I had no idea how you actually, I had seen it written down many, many times, but I just thought that you would say mortgage or something like this. It's actually mortgage. Anyways, we have n subprime mortgages, which means that we have lent money to people that unfortunately probably will not be able to pay us back. This is what subprime means in finance terms. In fact, we're going to assume that the probability that each borrower that we have lent money to buy their house, the probability that they default, which means that they do not pay us back, is 2/3, which is very high. Okay. And now, what we want to do is, we're a financial institution, we want to make money, we want to build a low-risk investment out of these subprime mortgages that we have. How can we do this? This sounds, it sounds difficult to do. Well, the idea is that we're going to build something called a collateralized mortgage obligation. What does that mean? It means that we're going to take our mortgages and we're going to separate them into tranches. These tranches depend on when the lenders corresponding to the mortgages default. The tranches, which are just, again, portions of our mortgages, suffer losses sequentially. So if less than 10% of the lenders default, then only tranche 1 is affected. The other tranches are fine. Okay? So we're basically putting into the first tranche essentially the people that are defaulting first. If between 10% and 20% default, then tranches, I'm probably completely mispronouncing tranches, but I'm not going to stop the video and go look up how that is said. So sorry about that. Tranches 1 and 2 are going to be affected, and so on and so forth. So the last tranche, tranche 10, is amazing. It's called the senior tranche in financial lingo, and it only loses money if 90% or more of the lenders default. So we can already see that it's a much more secure investment than the others. And our goal here is going to be to estimate the risk of the senior tranche. Estimating risk in general is of enormous importance in the financial industry for obvious reasons. Let's start with a model where we just say, okay, we know that these borrowers are going to default with probability 2/3. We're going to assume that they default independently because they each have their own life. They just default if things don't go well with probability 2/3, but it's all independent. In that case, the number of defaults among our n lenders is going to be a binomial random variable with parameters n and parameter theta equal to the probability of default, which is equal to 2/3 by assumption. Now, if we're interested in the probability that the senior tranche loses money, we have to see what's the probability that that binomial has a value that is greater than 0.9 times n. Here is where the central limit theorem comes in. We're going to approximate this binomial as a Gaussian, as we explained in the video on the central limit theorem, the central limit theorem tells us that if a binomial has parameter n for relatively large n, we can approximate it as a Gaussian that has mean theta n and this standard deviation, which means that if we standardize this quantity that is binomial, then it's going to have a distribution that is Gaussian with mean 0 and standard deviation equal to 1. Okay, and here on this side, we have the results of the standardization on the other side. If we plug in theta equals to 2/3 here, we have that this is the probability that a standard Gaussian is greater than 0.9 times square root of n. Okay? For n equals just 100, this probability is extremely small. Okay? So, which essentially means that the senior tranche never loses money. Let me show you a picture. This is the distribution for n equals to 100. We see essentially that the number of defaults is approximately Gaussian at 2/3 times 100, and that the variance has been reduced, as we know, by a factor that is linear with the number of mortgages that we're averaging. So we're essentially exploiting this knowledge of the central limit theorem to make this variance small enough by averaging over 100 lenders so that the probability that we end up here with more than 90 of the lenders defaulting is essentially 0, which means that the senior tranche suddenly is an extremely low risk investment, even though we started with all of these subprime mortgages, each of which is an extremely risky investment. Okay, so hopefully that logic makes sense. And this is why before the 2008 financial crisis, a lot of people decided to give a lot of mortgages and loans, sometimes only based on interest, without any documentation, and so on and so forth. I took this picture from Wikipedia. In fact, at some point, it says here that about 23.5% of all mortgages were subprime. So there was a lot of subprime mortgages. People were being lent money to buy houses, even though there was a high risk that they wouldn't be able to give the money back. What could go wrong? People made a lot of money out of this. Well, what could go wrong is that we had the financial crisis. If you want to know more about this, I really recommend the book, The Big Short. I really enjoyed it. Very entertaining, also very informative. But the point is that the risk of these subprime mortgages was not well evaluated. Here I want to emphasize that the models used to evaluate the risk of these subprime mortgages actually did not assume independence. I don't know anything about finance, but my friend Danny, who works estimating risks for a bank in Luxembourg, was kind enough to kind of take a look at my slides and so on. And this is what he pointed out. Like, this is, like the main idea is true, which is that the risk was not well estimated. But it's important to emphasize that those models were not like our cartoon example. Okay, they did incorporate dependencies. Anyways, now let's look at an alternative model for our cartoon example, where we include a very simple dependence into the model. We say that the defaults depend on the economic context. How do we model the economic context? We model it with a random variable r that tells us whether there's a recession or not. If r is 0, then the economy is strong. Everything is fine. If r is equal to 1, then there's economic disaster. And what we're going to say is that the PDF of whether there's recession or not is equal to 2r between 0 and 1. Why have I picked out this particular PDF? We're going to see in a moment. The reason why I've picked that PDF is that now, if under our model we assume that each borrower defaults with probability r, and we compute the distribution of the probability that each borrower defaults, well, the random variable that represents whether a borrower defaults or not is a Bernoulli random variable b with parameter r, if we condition on this event, okay, that this economic context is equal to a constant r. But now we want the probability that the borrower defaults. We need the marginal of b. In order to obtain the marginal of b, if you remember our video on discrete and continuous random variables, what do we need to do? We get the conditional PMF and we integrate it weighted by the marginal PDF of what we're conditioning on. And if we do that, we get r times the PDF, which is 2r. We have to integrate 2r squared from 0 to 1. That's just 2 times r cubed divided by 3 from 0 to 1. It's equal to 2/3. So by choosing that particular PDF, I obtain the same probability of default for each of the individual lenders. Okay, so in that sense, our model is also consistent with this observation that the lenders, each of them default with probability 2/3. But the model is very different to our first model because now these lenders are connected through the economic context. So now let's take a look at the probability that, let's evaluate the risk of the senior tranche under this other assumption. We're going to assume that other than the economic context, there's no other dependencies between the defaults. They're all conditionally independent given the economic context. Condition on R, the number of defaults is binomial with parameter n and r, okay, because each of the lenders default with probability r. So now, in order to compute the PMF of D, we again do this thing where we look at the conditional PDF and we integrate it against the marginal PDF. There has to be a typo, of course. Okay, it's not a very serious typo, but I'm a bit OCD, so let me put dr there. So now we plug in the binomial there, and we multiply it times the PDF, and now we integrate this. We're not going to do it by hand right now, but basically the integral is equal to this expression here. Okay? You can do it on your own if you want. How does this look like? Let's take a look. For when we simplify it, we get this expression. If we plot it, we get a very, very different distribution for the number of defaults, where you can immediately see that the probability that we get more than 90 defaults is actually non-negligible. Why is this happening? This is happening because when the economic context is bad, all of the lenders default at the same time. When the economic context is good, then they don't default also at the same time. So we get the same probability for each individual lenders, but now there's this huge dependence where they're all defaulting if there's economic catastrophe, which, by the way, is what happened in the financial crisis. What's the probability that the senior tranche loses money? We're not going to compute this, it gets a little bit complicated, but it's basically equal to 0.187 for n equals 100. And interestingly, if we push n as large as you want, it actually converges to 0.19. So it doesn't work anymore that if we take more lenders because they're independent, the probability that just 10% of them default is actually really small. This phenomenon doesn't hold anymore because of the dependence with the economic context. In this case, we're always going to have about 20% probability of them defaulting. Okay, this probability is not going to be pushed down as it is when we assume independent defaults due to the central limit theorem. So 20% of the time in our simple model, we get economic catastrophe like the one which happened in 2008. And that's all I got. What have we learned? We have learned that independence assumptions can have enormous influence on risk estimates. And we have also learned that this Gaussian approximation provided by the central limit theorem only holds under this assumption that we're summing independent quantities. Thank you very much.